All right, this is a light pre-lab video for you guys. We have two different types of experiments, and not really experiments, but two different type of activities that we're going to be doing today. One of them is not with that, but with this, a flame test, and the other one is going to be an emission spectrum, not really a test, but more of an activity, like I said. Okay, so with the flame test, what you're going to be doing is you're going to have a little wood splint. Okay, imagine like a little, very, very small, thin tongue depressor. And you're going to have like a sludge of a concentrated salt of various compounds. And what we're doing is we're going to pretty much put some of the sludge and mix it around like you're stirring the sludge. And then you're going to put that end of the sludge into a Bunsen burner, and you're going to make note of the different flame colors that come off of the splint that has been saturated with that particular chemical. And what we'll notice, hopefully, is that the different chemicals will produce different flames, flame colors, and then you'll write in, sludge A was, or solution A was this color, solution B was this color, and then you'll just have those notes down. The emission spectrum activity is a little different. In class, we learned about an emission spectrum, which looks something like this. Okay, so what we're going to have is we have four different light lines that show up on a diffraction grating when you look through it, and you'll see it when you look into an emission tube. So what we'll have is, you guys saw these in class, right? A little tube looks like this, right? And I ran electricity through this, and it caused a light to form inside here. And what was happening is the excitation of the element that was in gaseous form inside the tube was causing electrons to shoot up to higher energy levels and fall back down, which of course was giving out color. And when you look at this light with a with a diffraction grating, which is pretty much a little piece of cardboard and has a little clear film in there, it's literally an inch by inch piece of cardboard with a little diffraction grating or a little clear plastic thing in the middle. You'll put this up to your eye, and you'll look at this light. Okay, so you'll look through this at the light. Okay, that's my eye. My eyes are blue. There we go. So you'll look through this, and this is close to your eye. The diffraction grating is close to your eye. You look at this, and you'll see the emission tube. You'll see the color there, but you'll also see on the side, to the left and to the right, you'll see these little emission lines. Okay, so see like this one right here, this one right here, this one right here, and this one right here. Now, why this color is there at that side doesn't make much sense to me. I think it's just a bad image. But anyways, that doesn't really matter. What matters is you're going to see some lines over on the side. And what you'll do is for each of these lines, you're going to draw them out. And there's only going to be 3 of these tubes, so it's not going to be that many to draw. But you'll have the 3 tubes, and for each tube you'll have an emission spectrum to draw, and you're going to want to label which colors are which when you look through them. Okay, and multiple people can do this at once. But the steps, or the task that you're doing here, is you actually have some math to do. And what you're going to do is, for this particular wavelength of light, which is 656 nanometers, you're going to determine the energy of that light. Okay? So I'm going to go ahead and pick on a different value, probably one that's not listed here. Let's go with, say, 500 nanometers. Okay, so for our example, we're going to do, I have a 500 nanometer wavelength of light, and I want to know how much energy is going to be be traveling along that light, or traveling with that light. So, or is associated with that light. I'm going to have energy equals hc over lambda. Now, lambda is wavelength, h is Planck's constant, and c is the speed of light. So, h is a constant. It is Planck's constant. Are you going to need to know the name Planck's constant? No. But the value, you don't need to know either, because I'm going to give it to you because it's a constant. Okay? That is 6.626 e to the negative 34. And c, which is the speed of light, is equal to, I actually didn't put the equal sign there, is 2.99 times 10 to the 8 meters per second. Okay. Well, nice thing is, whenever I multiply a constant by a constant, i.e. h and c, the product of those two things will also always be constant. So in this case, my my product is going to be 1.98 e to the negative 25th. I believe. Let me double check that. Okay, sorry, correction. 1.99 e to the negative 25th. Okay. And then this is going to be in joules per meter. Okay. The bottom wavelength is in meters, but if you notice, I have nanometers. So you'll have to do a dimensional analysis conversion first. Remember that there is 1 billion nanometers is equal to 1 meter. So if I do my conversion, which I expect you to know how to do, I'm going to end up with, let's see, 5.0 times 10 to the, or I'll go ahead and keep consistent with E, I guess. E to the negative 7 meters. Okay, so when I do my math, my meters are going to cancel out, and I'll be left with joules, which works out because I want joules, because joules is a unit of energy. So if I have 1.99 times 10 to the negative 25th, and I divide that by 5.0 e to the negative 7, my final answer is energy is equal to 3.98 e to the negative 19 joules. Okay? You will have to do this calculation for, let's say, 1 emission line, 2 emission lines per emission spectrum. So you'll have 3 tubes that you'll look into. Each one's going to have an emission spectrum, right? So 3 tubes at 2 calculations per tube. That means you end up with a grand total of 6 calculations, which should be ample practice to solve these types of problems. Okay, so you'll look at the emission spectrum, okay, draw it out, pick any 2 lines, determine what the wavelength is in nanometers, and then convert that nanometer into meters and plug it in here. Use the Hc constant, which is 1.99 e to the negative 25th joules per meter. Put that over the wavelength in meters, and you'll be left with energy in joules. To make sure you're doing it right, for any visible spectrum line, the energy should be with that exponent. Okay, if it's not with that exponent, then you're probably doing your calculation wrong, or you're entering in your calculator wrong. Either one, be sure to ask me.